Okay, so we talk about errors and then we jump to functions. So that means we skip some chapters from the book that is also in the schedule, I mean the syllabus as well. So we talk about errors already, and then after that 6 and 7 we skip. So if you're interested, you can go ahead and read those things. They're talking about electrical service circuits and so many other things in there. And now we're going to talk about functions, which is a chapter 8. Okay, so the chapter 8.2, that is where I'm going to start. And the next is empirical models we're going to talk about, right? So we jump to chapter 8.2. So there it is. Okay, right. So well, in here you will learn some the fundamental functions. Well, why the functions are important. Well, you are actually design some the graphs using Vensim, right? So you should know what are the depending on the shapes you get, what kind of a function it is. So that is the main idea, that we jump into functions. Okay, so let's talk about that now and move on from here. Okay, so what are the functions out there, right? So basically you have several types that we're going to look at today. So these are depending on the data that you get, and then you formulate those, and then you come up with different kind of shapes of a graph. So that is how you whatever you see in there will be falling into some of these functions. So the linear function is something that you have already seen in your high school math, polynomials maybe, right? And then we're going to look at square root functions, exponential functions. This is one thing that is more oftenly coming, especially when you're talking about phenomenons, right? And then also logarithmic functions. I will go through that. We already know what is logarithm is. We discussed that earlier with the irrational numbers. And then trigonometry. Very rarely used in many of these subjects, but in mathematics it's very often using these functions as well. Okay, so now let's talk about these types. Okay, right. So this is a linear function, and the linear function means that you usually get the graph with a straight line. So that's what it is. So this is the definition. You may have seen this equation, right, in many times. So we have two unknowns in this one, right? And let's look at that. Right. So what we have here is y equals mx plus b. So what is this m here, right? And then what is this b here? Those are constant values for the given graph, right? How do you calculate that? Well, usually when you are having a graph with a straight line, right, in order to define a straight line, you have to have 2 points, right? So maybe 1 point here and 1 point here, right? So this point you can say x1, y1, and then the other one I can call x2, y2, right? So those are 2 points in the graph, let's say like that, right? So joining these lines like this will give you a graph. So in this case, if it is a straight line, you call linear function, right? So that's what it is. And then well, in order to satisfy this condition, you can say this line right here will go through this one, and also this line is going through this point as well. So it has to go on 2 points. So that means this number has to satisfy this condition and this number has to satisfy this condition. So that means you can have two equations. One, you can say y1 equals mx1 plus b, right? And then the other one I can say y2 equals mx2 plus b, right? So I can call this number 1, I can call this number 2. So those are two equations I can generate with a linear equation like this, which is going on these 2 points, right? So why I'm doing this? Well, I want to find what is M and what is B, right? So I have two unknowns, two equations. So how do you solve this is, if I subtract 1 from 2, right, or other way around, 2 by 1, let's have it consistent with the equation they're talking about. So I'm just subtracting 2 from 1. So what I get here is the inside I get this, right, and then that will be equal to, well, when you subtract one from the other, this b to this b cancel off, so I will get m x2 minus m x1, right? So what this means, I can take off the m out and I can have x2 minus x1 in there, right? This will be the same. So in that case, okay, so if I divide both sides by this value, I get here x2 minus x1, and then this side I get x2 minus y1 divided by x2 minus x1, right? So this to this cancel out, so the m will be equal to this value right here, right? So that is your m value. So if you know the m, if you apply m here, obviously you can find the b, right? Yeah. So then you know what is the constant m and what is the constant b, right? And m usually defined as the slope, right? That's the slope of this this line. What is the slope? Slope is this angle actually, right? So that is the value it's equivalent to, right? So okay, right. So that's how the linear function is designed. If you have 2 points in there, you can obviously define the m and b, and then you can come up with the proper equation. Okay, so that's the thing. Those are the points that you should know about linear equation. Okay, and okay, so let's move forward. Right, so this is another one, which is the polynomial function. So I think you recall this one from our calculus review, that you were standing on a bridge 11 meters up, and you throw a stone up, and then the stone goes up and then come back down. So if you graph it, you can see this kind of movement on it, right? So what kind of a graph is this, right? So that is what is the function for that? Well, if you have done physics, you know that is a projectile function. In the projectile, we will have equation equivalent similar to this one, right? So this is what that gives you over time and the distance, right? So this is the equation for that. Okay, and so it will give me something look like this. When you mark it down, the height of our ball or the stone going up, and you measure that from the sea level, right? That's why you're starting with 11 meters, and by the time what is the height is, right? So when you graph this, I mean when you come up with a function for this, this is what is equal to, which is, it gives you something like what is showing here, right? Okay, so it is a quadratic function, that's why it's a t squared, right? The time squared, plus the 11 is the starting value right here, right? And the velocity is 15, showing there, right? And so on, right? So in general form of quadratic function, you can write it like this. This is a general form. So if I want to write more in it, I can say fx equals, let's say I have a little bit more here, Like for example, I have let's say 5, right, and x to the power 5 plus ax4, x to the power 4 plus a3, x to the power 3 plus a2, x to the power 2 plus a1, x to the power 1 plus a0, x to the power 0, right? So how do I match this one to this? Well, I can say a5 equals 0, a4 equals 0, a3 equals 0, right, and a2 equals minus 4.9, and I can say a1 equals 15, and x to the power 0 is always 0, so in that case a0 is just 11 in this case, right? So this is the general form, means you can write any number, right? You can write up to an, so the n can be any number, right? So but whenever the coefficient here, whatever the value in the front, will decide whether you want to keep this value or not. So in that case, these are the ones that you have here, and these are the ones you don't. Why this is 0? Well, if you multiply anything by 0, it gives you 0. So in that case, all these will be 0, right? So you don't have to worry about that. Okay, so that is what polynomial function is. Polynomial function means you will have some powers of x, right? And then you can define it. Actually, this is also, you can say, a quadratic function because it has x to the power, right? Okay, right. So let's look at another one. Right, so this is something they're talking about, the quadratic functions or the polynomial functions that add c. What happens if you add a constant to the what is the impact on if you add something like the constant to the y value, right? So what happens when you do that, right? So let's get a graph here and see what happens. So let me write it down up here. So let me have a function y equals let's say 2x squared, right? And then I'm going to plot this. How do you plot this? What is the shape of this? Well, I can give some y values, I mean x values, and calculate the y value. So I'm going to give -1, maybe -2, -1, 0, 1 and 2, right? So those are the values I'm going to plug in. So -2 means you apply -2 here, so it will be positive 4 multiplied by 2 is 8, so it's a positive 8. And then if I get -1 squared is +1 multiplied by 2, so I get 2 here. Well, if x is 0, everything is 0, so I get 0. And then again the 1, I get 2. If it is 2, I get 8, right? So if I draw this on a chart like this, right, what I get, 0, 0 position, and then the 1 and the -1 plus 1, 2 is somewhere here, 2 is somewhere here. But in this case I get a really big number for 8, and then 2 somewhere here, right? 2 maybe a little bit below, like somewhere here it's 2, right? Right, so if it is 1, it's 2. If it is 2, it goes to 8. And this way as well, somewhere there, somewhere here. So, and it's going through the 0. So it is something look like this, right? So that is your graph look like. This is a shape of a parabol actually. Right, it's starting 0 at right here. At this point right here it's 0. Right, so okay, so now, and it says okay, add c to each y value. So if my y value is increases a little, right? So in this case, I'm going to add the c into this. So what happened in that case? Well, if I add c into each of them, right? Let me get another color here. Yeah, so if I add another value to c and the c is greater than 0, that means obviously I get everything move up by z, right? So I get something look like this, right? So it is going up, the chart is going up. It won't change the y value because x value intact the same values, right? Because it doesn't expand x at all, but the y value is going up, so the chart will be move up like this. So in this case right here, this is what you get, right? If it is less than, so then obviously your graph will be look like this, right? The x won't change, but the y value is now changed, right? So this is what when you're having these kind of things, right? So what happens when you're having when you multiply your y value? So how does that affects, right? So so here it is when you're having something like this, right? So in that case, what happens is when you're having a graph like this, now when you multiply, the 0 multiplied by anything will be 0. In that case, it doesn't affect. But any other value, for example, I have the -1 here and -2, okay, and then this side 1 and 2, those will be the same, but right now I used to have 2 here, now it will be 2c, so somewhere here if I have this case, and 8c will be somewhere here. So in that case, your graph stretch on your y-axis, right? So your graph will stretch like this, right? So that's what happens if I have positive, right? So then what happens when you're having something is not that big, like for example, if I have something like this one right here, so that means if it is 8, let's say this one is 0.5, 0.5. So if I multiply this by 0.5, that gives me 4, right? Yeah. So in that case, everything will be shorter. So if it is 2 here, now it will be 1. If it is 8 here, now it will be 4, right? So it's like this. So that means your graph will shrink in this way. So it will be shorter on this length. So it will push down. So that's what happens if I have your c is less than 1. Okay. So if you have point values, obviously your y value will be shorter. If you have higher than z, it will be longer like this. Right, it's stretched up and it's stretched down. So that is the difference if I multiply those. Okay, so then let's look at what happens when you're having something, some values are applying to your the x value, right? So the first thing is, let's see the negative y. So your positive y is obviously I have some graph look like this, and if you multiply everything by negative, so in this case I have all the positive values, right? So if I multiply everything by negative, I get a mirror image of this, something like that. So it is just a flip look on that. So this is this situation right here. Okay, right, so that is this situation. So keep this in mind. I might test you on this in your exam. I will give you the original shape and ask what happens in each case. So make sure you learn this, right? So that's better, you understanding each of the steps that I just showed you. What happens if the c is adding the c positive, what happens when you're having a subtract c, what happens when you multiply, what happens if you have a negative value, and those things. So I will test you on this. So make sure you have an asterisk on this slide and understand the behavior of each. Okay. Right. So the last two here, I'm going to talk about what happens when you add c to the x or the t in this case, right? So in this function, actually, I should have write it like this to be consistent with it, t squared instead of x here, right? So this whole thing is talking about t because of that. So that's one remarks I had to make, because I just put x and y on the top. It has to be x and t because I mean the y and t, because I'm talking about t here, right? Right. Okay, so I want to point out a few things here. The one thing is, well, when it comes to right here, this one right here, right? So this is y equals ft, y by ft, so that will be equation will be equal to this right here, right? So in this my case, this is what it means. Okay, right, so this is the equation, and this is what it means by y equal ft, right? Okay, so the other point I want to point out is pretty interesting what we're talking about right here in this line, right? Okay, right, so let's analyze that. This means is actually we're going to calculate the y value with this right here, but when you're drawing the graph, we draw for t and y. Okay, so my graph actually I'm drawing for ft and t, but I'm going to add some constant here. But so when you calculate it, actually this is what you do in the calculations. So that is very important for you to know. So if so I want to calculate the y value or the ft, right? And this will be t plus c, and here is the t value. So my t values, I'm going to plot it with the t values, but I'm going to draw it with the t plus 1. So in this case, let's say -1, 0 and 1. So that's enough for figure out what's going on here. So if it is my equation is what, ft is equal to 2t squared. So if I replace this t by t plus 1, this is what I get actually, right? So this is what I get, right? So that will be a little bit bigger value for my y, right? So in this case, my y value will be t plus c squared in this case, right? Okay, so y, this is t plus c, means -1 plus c, so it's -1 plus c squared, and here it will be what, it will be 0, so it will be c squared itself, and here is a +1 c squared, right? Okay, so you can see now when the t is 0, right? So this is the place that I got before for the t0, but when in this case, when I get t0, right, and actually this is t plus, so these are the values here, which is c squared and 1 plus c squared right here. Okay, so you can see now this is no longer 0 anymore, right? So now I have something else here, so that means my y value is moving up to somewhere here, right? Okay, and yeah, so if it is -1, the -1 is somewhere here now, so it will be somewhere there. So you can see now my graph is obviously this one is less than c squared, so it will be somewhere here, right? So that is the value for that. And so whenever t is minus c, so that if the t is, if the t is minus c, right, that is where you get 0 here, right? C plus minus c. So that means my t has to be somewhere here when it's reached the 0 position, right? So my graph actually now look like this. So that's why it says it's moved leftward, right? Okay, only if I draw the graph between t and ft, yeah, it's moved leftward. So that's the leftward shift, right? Okay, so the positive c also, I mean, if you're talking about this, right, where is the y going to be 0? So the y going to be 0 when the t is equal to plus c. So that means somewhere here, if there's a plus c, then my y is, or the ft is going to be 0. So is my graph will be moved that way. So it's the rightward shift. So that's what it's talking about here, the leftward and rightward shifts. Okay, so that is something pretty interesting when you only plot the graph of the t with the ft, right? But you're adding some value here, means it's shifting, right? Okay, all right. If you're having a c, it will go up and down this way. If it is applying to your x, it's going left and right this way. And if you multiply that by these values, of course it will be shrink and it will be stretch, whatever it is, depending on the values, right? So those are things that you have to know, right? It's moving up and down, and it will change its shape. How do I do that? I can draw like this, right, the shape, and here it's moving this way or this way. So that's all, right? So if you know these things, that's enough. Just get an idea. This is the summarized idea of all the things I was talking about so far, right? Okay, so then let's look at another type, the polynomial function. This is a quadratic function I just explained. Now the polynomial of that I'm talking about here. This is the general form of a polynomial, the same thing that I pointed out a minute ago, right? This is the polynomial form of it, right? And then well, you can write this in this form, which is nothing but, here I have the pt, right? I can write this pt as a, this is power 3, right? So it's a cubic shape in there. So I can say a3 t3 plus a2 t2 plus a1 t1 plus a0 t0, right? So, and then I can apply some values to my a3 will be nothing but 1, and a2 will be in this case -4, and a1, which is nothing but -1, and a0 is 4. So I apply that to this equation. This means 1 multiplied by t3, right, -4 multiplied by t2, -1 multiplied by t, plus 1 multiplied by t0, right? So what is this? Means t3 minus 4 squared minus t0 is 1, so I'm sorry, this is 4, right? And then you get 4. So that is what, how do you come up with this one from the general form? This is the general form, this is the equation. Keep asterisk on this. I would ask you some questions related to this, okay? Right, so so that is a polynomial function, right? Okay, all right, so let's move on to another type, which is a square root. The square root is pretty interesting one. All right, one thing I want to point out here, what is square root actually? Let's say, how do I plot this? Well, it's still talking about the t and y. So if I have t values here, I want to calculate the y value. I can call this square root of t here, right? And in this case, let's say I have 16, I have 9, I have 4, I have 1, right? So the square root of this is plus or minus 4 actually, right? Yeah, and plus or minus 3 in this case, right? And this is plus or minus 2. This is plus or minus 1 actually, right? So if you consider plus or minus, because each of these values can have one of these, because one, if you multiply these two as well, you get 16, right? So I can make 16 in two ways, right? So actually if I apply these minus values, you're supposed to get something look like this as well, right? In this case we'll talk about non-negative real numbers. If it is a real number which is non-negative, well, that's the case, you get only this one. But keep in mind, square root function has two ways. Only if it is this, the absolute value you apply to this, in that case you get this value. If it is not, usually you get this whole thing, right? What I'm talking about here is 16 is somewhere far away here. Let's say 16, and then 16 gives you 4, right? Can give you minus 4 as well, and the 9 is somewhere here. So the 9 and 3 has to be matched, right? And then 4 is somewhere here, and I get 2 right here, and then 1 is somewhere here, and then I get 1 somewhere here. So if I plot these points, this is the shape I get. It is not a straight line, you can see that, so it has to be a curved line, right? It's like that. So it is so the concave down, you call it like this, and the increasing on concave down, so it is something look like that. So that is the graph shape for the square root function. If you ever encountered that in your functions or your Venn outcome, you know it is the square root function. Okay, right? So that is something gives you an interesting outlook like that, right? So let's look at another type, which is we're looking at next is the exponential growth. That is pretty interesting. It's getting high and high like this. So this is actually something which is related to population growth, right? Yeah, unconstrained growth and decay. We talk about this equation right here. That is something we talk about in that chapter. And well, it has some constant value and the initial or the previous p value, and then you have the power here, it's RT, right? So this is a constant for this occasion, and it is a variable actually. This is a absolute constant, which is a rate, right? And this one is actually the previous value. It changes depending on this one right here. So this one and this one is related, initial value, right? But yeah, you can take the initial value, any of it, maybe the starting value or something else, right? And then this one is a constant rate of growth, right? This is a constant value and this is the rate, right? Yeah, I'm sorry, my bad. So the R is the rate, and then the T is the change, which is the time on this subject that we were talking about, right? Remember, right? Okay, so this is a P0. It's the constant at the beginning. We saying, okay, it is 100. It's 100, starting with 100 here. So the only thing is, if it is 0, what happens? Nothing happens, right? So it has to have some value to the startup. That means some people has to be there in order to start growing this thing, right? So we were talking about bacteria versus time, and we put 100 bacteria in there and then let it grow, right? So by the time of this intervals, it's really growing really fast. Why? The first time it will be 2, the next time it will be 4, so it multiplies, right? It multiplies in some crazy way, like that. So it's pretty interesting There's a story behind it. When somebody, I don't know whether it's authentic story, it's just by reading I learned this story about the person who introduced chess, right? So the chessboard is like this, and it has 8 squared on the one side and 8 squared on the other, right? And okay, so he teach this chess game to his king, and king got surprised and interested, and he said, okay, name something that you really want from me as a gift for introducing me this wonderful game, right? So what he said is, well, I will get one single grain on my first square, right, and 2 single grains on my second, and square it for the third, right, and square it for the fourth, right. So each time square the number that you have, and then fill this whole chessboard with that and give me that, right. So it is a 2 to the power actually, right. 2 to the power 0, 2 to the power 1, 2 to the power 2, 2 to the power 3, 2 to the power 4, and so on. So he asked him to do that. So it will double the whatever the value is, it will be doubled, right. So in this case, when it comes to here, it will come up to some one bucket of, and then next one it will be 2 buckets, like that. So on, it will be always get the power of the value, right. In that case, you get a huge number when it comes to here, right. And they did not have enough grains to fulfill these 64 squares, because it doubles each time when it comes to each square, right. Doubles from the previous value. It's the same thing right here. So that's exponential growth. So they didn't even have enough grains to give him even in his whole country. So that is how much it counts. The king laughed and said, okay, this is a simple gift that I have to give you. And he ordered his servants to give that, but they could not fulfill the requirement, right. That will be a really, really huge number, right. Okay, so that is how the exponential growth is all about, right. So it will be a very big number at the end, right. Okay, so this is a 2, this is 4, and this is, this is 2. Next time it will be 4, next time it will be 16, next time it will be the power of 16, power of 2 of 16s. So each time it will be grow like exponential value, right. So when you think of something like that, it will be a huge number at the end, right. So the next time it will be this, next time it will be this, also like that, right. And the next time it will be this, so on. So when it comes to that, it's a huge number. Okay, right. So that is one story behind, to understand what is exponential and how it grows, right. Okay, right. Here they're talking about the bacteria growth. So you can see how this graph behaves, right. So that is something which is not good for many things. If it is an exponential growth, it will grow really fast, right. Okay, if it is a disaster like the bacteria growing and harm people and things like that, it's not good if you're having seen an exponential growth. It is good if you're having a profit making as exponential growth, of course. But when it comes to economics, if you can do the exponential growth on your business, that will be great, but not for many things like these kinds, right. Okay, right. So the exponential growth means if you have something in this order, the power, okay. that grows really fast. So this is the x value or the t value in this case, and it is a constant time t to the power, right? So that is very big number when it goes over the time, right? So that's called exponential, right? This is polynomial. We have a power, a constant power here, but this one has the variable power, right? This is changing the value by power. So let's look at the difference. Okay, so this one is quadratic or the polynomial, this one is exponential. So you can see the difference, right? Make sure you understand the difference. This is a to the power, this is 8 times. Okay, right, so that's the only thing that you have to keep in mind in this one, right? Okay, so let's look another one, which is, oh, we are going to talk about logarithms, right? So the logarithms, we already know some of it. Well, what is a logarithm? Well, this is a good example here. What this means is base 10, so that means 10 to the power 3 is equal 1000, right? We already know this, right? So so that means if you want to write this in a log fashion, you can say the 1000 made by 3 of base 10 to the power. So you can reverse this when you're writing it. This is how you write, right? So how do you really remember this? You can have a bird beak like this, or the Tarzan like this. So what this means is 10 to the power 3 is equal 1000. So that's the order when you're writing. So Tarzan is good way of writing it. 10 to the power 3 is equal 1000. Right, so remember it like that, so it will be easy for you. So 10 to the power 6 is equal million, right? 10 to the power 6 is equal million. So that's what it is. So look at the Tarzan like this. Tarzan hang on a string and then go up and away. So he's jumping off the at the branch, and there is a string like this, and then he jump off, so he will go like this, right? So that's the idea of here. So it's easy for you to remember, because when the Tarzan jumps, so this is how you go. So that will help you to remember base 10 to the power is equal to the value, right? So that's what the log means, right? Okay, so yeah, that's the easy way. I was talking about this before, so you know. Or you can go with the bird beak, of course. The bird beak is like this, and then that's also give the same idea, right? So the natural log means the base. So this one is a base 10 I was talking about, right? But natural log is base e, right? So we talk about that as well, or it's a irrational number, or the Euler number. So e, we just write this as ln, right? So this is what it is, right? Okay, so that means ln n equals m means n is equal to e to the power m. Right? Yes, the same thing. So it is e to the power here. So if you write it like this, that's e to the power m is equal n. This is what it is, right? Okay, so let's look at the graph, how the graph look like on this. Okay, right? So yeah, so let's look at the graph, how the graph is look like on this. So this is a logarithmic function, and then only thing you have to do is just remember this. These are negative values, and whenever you have the log values, it will be look like this. So you know, one thing is logarithms not reaching more 0 in this case, right? For the positive axis, it will be like this. but for the square root of log, I mean the this is what it is, and then well, this is a square root function obviously, and this is a linear function. We already seen that one, and so this one shows you actually when the x and square root x and the linear x, how those three are look like, right? Okay, so we already know this one, right? Look at this one already, and the square root of that, and then so I can say this one is something look like mx, right? This is y equals mx. B is 0 because it's going through b0, and this one is y equals square root of x, and then this one is y equals ln x, right? So these are the graphs you get for each of it. Okay, right? So just have a little idea on that, the shapes, and then you good to go, right? So the last one here are the trigonometric functions. So this is actually one cycle. So one cycle means when you're having this angle increases, right? So it increases means this one will move along with this line like this. So this will make a circle, right? And what is actually sine, cosine, and the tan? So this is what it is. So this is the sine function. So if I have a sine function, what is sine is? Well, the sine is nothing but if I have an equation like this, if this is 1, right, if this angle, whatever the angle it is, so then if I call this theta, for example, sine theta is equal to nothing but the y value divided by 1 in this case, right? And the cosine theta will be equal to this value, which is nothing but x value divided by 1. Okay, right? And well, you can see one thing. Usually in this kind of right triangle, you know, this length is always shorter than this length, and this length also shorter than this length. What does that mean? That means these values never exceed 1. Okay, so it will be always less than 1 or equal to. Okay, so keep that in mind. These guys cannot exceed 1. So that's why in sine, right, in sine even you will have it between these two values. In the cosine also you have it between these values. So the maximum value it can go is 1, minimum value is going to be -1, right? So +1 and the -1. So it will be stuck in that range, right? And whatever the theta is changes, these are the theta values, right? This one will go around. So you can see it hits 0 at once here and another time right here, right? So the y value will be 0. I mean so the x value will be 0 in two places, right? So that is also interesting. When you're drawing this one, you can see those the changes here, which is 1 0 1 0. When it come back to again, you can see a 0. So that means when you're moving it along with the values like this is what you get, right? Okay, so this is the other one, which is the cosine value. So this is what it is, and you can see it is the opposite of this, right? In here, this is actually 180 divided by 2, which gives you 90. When it is 90, right, the sine 90, that means I'm always getting a value somewhere here, right? Okay, so So that means this angle is 90 degrees. So if it is 90 degrees, I actually get the value of 1. So that is the maximum value I get for the y right here. So let's get 1 right there, right? Okay. And again, when it's negative value, so right here, it's getting -1, right? Okay, so then there are two places it's reached the 0 of the y value. So that's what here, and then again when I come back, that's here. So this is a perfect circle, and you get starting point 0, and again cross back, come here, and the 0. So it will cross another 0 at the beginning, right? I mean in the middle. And here you can see when it is 90, of course this value is 0. So in that case, whenever it's 90, in the cosine value, it's reached the y axis to 0. And again, this is the opposite of this, right? Okay, so when it's reached 0 in this case, it's reached the maximum value in this case. Okay, so you see that? So that is the comparison on this, to sine and cosine, right? This is the opposite of this, right? But when it comes to the tan values, it behaves somewhere very crazy. Like for example, tan is nothing but the sine theta divided by cosine theta, right? So this is what the tan means, right? So the y divided by x, you can say this. Why is that? Well, I said here sine is this divided by cosine is this, right? So this is nothing but y divided by x, right? Okay, so one interesting part here is what happens when the cosine is 0, right? When the cosine is 0, that means where is cosine is 0? Cosine hits 0 at pi over 2, right? So the pi over 2, I have two values here and here. So we don't have any value for my, when the cosine is 0, this is y divided by 0. That is what? It's undefined, or you can call this infinity, right? So that's why it's never going to end. So this will go forever, but never touches this line. It's never going to touch this line. In this case as well, it's never going to touch this line because there's no definition for this value, right? Again, it's coming back. This is never going to touch this line. So there is always a gap between these two. There's always a gap between these two, and these two. Right, so it's a weird graph because of that. Why? Because there's no definition for y divided by 0, right? So it will go off on these points right here. Right, so that is one interesting conclusion when you come to look at this and you apply this. Obviously it will go 0 when y is 0, right, at these points, but when it comes to the 90 degrees, there's no definition for tan. Okay, right, so those are the functions I'd like to point out here and the behavior of it, right? There was a one I just skipped on the notes. Let me look at it. I'm not worried about that. On the functions, let me go down on that and talk about a little on it. That what I skipped actually. Not the logarithms. Yeah, this one, the logistic function. So the logistic function they're talking about here is you know, the population growth with the carrying capacity we have. If you want to put this in analytical solution, this is what it look like, right? And we're talking about the t value here. The growth on this one is actually, if you have the capacity to range stop in there, you can go and look at it in the chapter 2. Obviously we had some graphs. This is the graph look like, right? Did you see? Do you remember this one? So this is the graph look like when it comes to those kind of functions, which is a logistic function, right? Okay. Actually, this one right here. Okay, so that's we look at this before, and it will always stop at maximum carrying capacity. But that is not a graph type. It's just talking about that. So that's why I didn't. I mean, it's not a function type. It's just a logistic function. It's talking about here as well, logistic function. So this is what logistic function is look like. Okay, so that is all I had to point out here. Okay, so I will look at empirical models next time. So right.